All right, so this is part 2 to section 10.2, calculus with parametric curves. So just at the top here, I've written up the formulas that I'm going to reference back to. It's the first and second derivative for the parametric curve. Let's jump right into the example because this one takes a minute to do. So we have a curve C is given by parametric equations x is equal to t squared, y is equal to t cubed minus 3t. And we're going to go through a couple different parts. The entire point of this example is so that we can graph this. So we're going to use the information about the derivative to do a graph. So A is to show that C has two tangents at the point 3, 0. So you might be worried here at this point. I'm going to jump back to my page before this. But I'm going to go up here. You can see that this graph I drew for part 1, I drew this like this on purpose because if you look at this curve here, this second point here that I guess it's the third one that I blocked in. Going through it the first time, I'm going up and to the left. And then I, go away from it. And when I come back to that point, I'm going down to the left. So that point right there is going to have two different tangent lines. So there's no problem with a curve having two tangent lines. So let us figure out how to handle that. So, we want to show that it has two tangent lines at 3, 0 and find the equations. Find their equations. So let's first start off by calculating the derivative. So I have dy dx is equal to dy dt over dx dt. And again, remember y is equal to t cubed minus 3t, x is equal to t squared. So I can do these derivatives pretty easily. Dy dt is 3t squared minus 3. Dx dt is equal to 2t. That tells me then that dy dx is going to be equal to 3t squared minus 3. This is scratch work, so I'm going to box it off. 3t squared minus 3 over 2t. And then I'm going to go ahead and simplify this a little bit just because we're going to need this a little later. So this ends up being, when you break up the numerator, 3 halves t minus 3 halves 1 over t. So that's going to be my derivative there. And now we want to, so now what we're trying to do is we're trying to show that the curve has two tangents at, the point 3, 0. The problem here is, I'm given the x and y coordinates of the point. I'm given x equals 3, y equals 0. So I'm going to write it like this just to kind of motivate what we're about to do next. So I have the x equation and the y equation, but I want the value of t because my derivative here is in terms of t. So in order to do that, I'm just going to take the equations for x and y, and I'm going to set them equal to 3 and 0 respectively. So because x is equal to 3 and x is equal to t squared, what I'm going to set up is 3 is equal to t squared, and that's my x equation. And then y is equal to 0, and the equation for y is 3t squared minus 3. Equation for y is t cubed minus 3t, sorry. Put in the derivative there, so it's t cubed minus 3t. This first equation is pretty simple. We're going to get t is equal to plus or minus square root of 3. Second equation, still simple, but a little more work. You get 0 is equal to t times t minus t squared minus 3. So I'm going to get t is equal to 0, and t is equal to plus or minus radical 3 when I solve the t squared minus 3 equation. So now what I'm interested in is what do they have in common? Because I need x equals 3 and y equals 0. If only one of them equals, 3 or 0, it doesn't matter. Because I need them both equal to, I need x equal to 3 and y equal to 0. So what do they have in common? If I look at that, that tells me that these two have the t equals plus or minus square root of 3 in common. So that tells me this is going to let me find the slope now. So what I can do now is I can do dy dx. And so actually what I'm going to do, I'm going to go ahead and calculate this. At t is equal to square root of 3, dy dx is going to be equal to 3 times t squared minus 3 over 2 times t. So this ends up being 3 times 3 is 9, minus 3 over 2 square root of 3. This is 6 over 2 radical 3. This is 3 over square root of 3, which is the square root of 3. So the derivative there is the square root of 3 at t equals square root of 3. At t is equal to negative square root of 3. I'm going to get dy dx is equal to 3 times negative square root of 3 squared minus 3 divided by 2 times negative square root of 3. And this is the same equation as above with just a minus sign in the bottom, because when you square that term, then that minus radical 3 squared, that's going to be positive 3 in that case. So when you do all this math, what this ends up coming out to is negative square root of 3. And now I can write down the equations of my lines. So let's use the equations of the lines. So we have slopes and we have a point. So we're going to use point slope form. So I have the point, 3, 0. They both go through 3. This is for both of these slopes, so the point is 3, 0. So I'm going to use the equation y minus y0 is equal to m times x minus x0. So for the slope, m equals square root of 3. What I'm going to get is I'm going to call this y1 minus, so y1 is going to be a variable here, so y1 minus y0 is 0. It's equal to m times, so we'll just use x and y. And remember that these are two different lines. So at m equals square root of 3, I'm going to get y minus 0 for the y minus y0 part, because again, y0 is 0, is equal to m, which is the square root of 3 times x minus x0, x minus 3. So this gives me y is equal to the square root of 3 times x minus 3. And similarly, for m is equal to minus radical 3, my points are the same. My slope is what changes. I have now minus square root of 3. So this gives me y is equal to minus square root of 3 times x minus 3. So that's part A. It's finding the equations of these tangent lines. So I just want to kind of recap, because this is the first time you've probably seen this. So what I did first is I calculated the derivative and noted that the derivative is all in terms of t, whereas I'm handed an x and y value. So from that, I took the fact that I knew the x and y values, I plugged them into my parametric equations up here, and with that I was able to solve those equations and get the values of t where x was equal to 3 and y was equal to 0. I took what was in common because I need both of those things to be true. I need x equals 3 and y equals 0. That gave me, this happens at time plus and minus radical 3. So from that, I was able to determine slopes at those two different times. And from those slopes and the point that I had, I just used the equation of the point slope form of the line to get the equation of the tangent line. Part B is to find where C has horizontal or vertical tangent lines. So let's go ahead and figure this out. So let's do the horizontal first. So this is where dy dx is equal to 0, and dx dt is not equal to 0. So if I just set dy dx equal to 0, so you remember that dy dx is 3t squared minus 3 over 2t. If I set that equal to 0, I can see that, at t equals 0, the bottom is 0, but the numerator is not going to be 0. So I can go ahead and just write this as 3t squared minus 3 is equal to 0. If I divide everything by 3, I'm going to get t squared minus 1 is equal to 0. This has solution t is equal to plus or minus 1. So I have horizontal tangent lines at t is equal to plus or minus 1. Let's go ahead and figure out the x and y coordinates. So let's figure out the points where that happens. So at t is equal to 1, x is equal to t squared, so I'm going to get x is equal to 1. Y is equal to t cubed minus 3t, so I'm going to get 1 cubed minus 3. This is minus 2, it looks like. Is that right? Let me double check the parametric equations. T cubed. Yeah, that's fine. Okay, so that's when t is equal to 1. T is equal to minus 1. I'm going to get x is equal to t squared. So I'm going to get x is equal to negative 1 squared, which is 1. And I'm going to get y is equal to negative 1 cubed. And again, this is going to be, so minus 3t, so minus 3 times negative 1. This is negative 1 plus 3. This is 2. So the points where I have a horizontal tangent line are at x equals 1, y equals negative 2, and x equals 1, y equals 2. This one happens at t is equal to 1, sorry. This one happens at t is equal to minus 1. Let's do the vertical tangent line now. So yeah, this is a really long example. So the vertical tangent line is where dx dt is equal to 0 and dy dt is not equal to 0. Otherwise, I would have a 0 over 0 situation, and I would have to determine that limit. Okay, so dx dt is equal to 0, dy dt is not equal to 0. Dx dt is 2t. Dy dt is 3t squared minus 3. We already know that's not 0 at t equals, so this one gives me t equals 0. And we already know that this dy dt is not 0 at t equals 0. So I don't have to worry about doing any limits here. So a vertical tangent line at t equals 0. When I plug that into x is equal to t squared, y is equal to t cubed minus 3t, I'm going to get x equals 0, y equals 0. So my graph has a vertical tangent line at the point 0, 0 when t is equal to 0. Part C, determine when C is concave up and concave down. So in order to determine concavity, we need the second derivative, d squared y dx squared. You can check the top of the page. I will try to remember to post these notes, but this is d dt dy dx over dx dt. So I have d dt of, so before I simplified, after I simplified the dy dx, this was 2/3 t minus 3 halves. That's right. Sorry, trying to do this off the top of my head. 3 halves t minus 3 halves, 1 over t. So that's the top. Bottom is dx dt, which is 2t. So then this is equal to 3 halves plus 3 halves, 1 over t squared, divided by 2t. So numerator is always positive. So So you can check, no matter what you plug in, that's always going to be a positive number. Denominator changes signs at t is equal to 0. So, you know, if you're a negative number, this whole thing is negative because of the t downstairs. If you're positive, the whole thing's positive because the t downstairs is positive. So if t is less than 0, we're concave down. And if t is greater than 0, concave up. What part are we on? D. Part D is to sketch using this information. All right, so I'm gonna have to, you know, be going back and forth between all of this. So first thing we should note is, let's do our vertical tangent or horizontal tangent lines. So the horizontal tangent lines were at 1, -2, and 1, 2. So we'll call this 1, 2, -2. So at these points, I have horizontal tangent lines. And you'll remember that, you know, this graph here, when you're close to the point where you found the tangent, your graph kind of looks like the tangent line, which is why we're doing this. The next one we had, so this one was at, so this top one was at t is equal to -1. This was at t is equal to 1. So this will help us with the concavity. At t equals 0, we are at the point 0, 0, and this was a vertical tangent line. I also had that the point 3, 0, the point 3, 0 had two tangents going through it at different times. So I'm going to connect all of this. So going from t equals 0 to t equals -1, we need to be concave down. And then t equals 0 to t equals 1, we're concave up. We stay concave up and concave down as we continue on. And then I have to go through this point with a positive slope there. And I go through this point with a negative slope there. And this is what it's going to look like, you know, as time progresses. You know, let me do that in a different color because I think that looks a little better. You know, this is the direction I'm going as time progresses. And remember, that is, you know, a feature of these parametric curves is these when these are drawn, they have a direction. And so that's going to be, you know, a really rough sketch of what's going on here. So I'm going to stop this video here. We're going to do another example about derivatives and then move on to integrals. So this is kind of a long section where a lot of examples, a lot of stuff to talk about. So I'm going to stop the video here.